Hello everyone and welcome to another Würth Elektronik webinar. My name is Markus Ebel and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is REDCUBE, everything about high currents on the printed circuit board. Our speaker is Stefan Bechle, who is working as Field Application Engineer at Würth Elektronik. He will hold today's webinar and also answer your questions. Before we start with the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. Today's webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. And if we are unable to answer all your questions within this time, we will answer them via email after the webinar. And if you still have any other questions left, just email us at isos-webinar@w-online.com. At the end of the webinar, you will be asked to participate in a feedback survey. Of course, we would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will also receive the link to the presentation as well as to the recording of today's webinar only in the next few weeks or the next few days. And now I will hand over to our speaker, Stefan, and I wish you an exciting webinar.
Yeah, thank you very much, Markus. Good morning, everybody. So I'm very happy to have you here today in our webinar. My name is Stefan. I work in the Würth Elektronik company now for 10 years. I started in 2011. And my task in the company is a field application engineer for the electromechanical parts in the south of Germany. What's electromechanical parts? All about switches, all about connectors and assembling products and power modules. So today I have a topic for you about our REDCUBE series, everything about high currents on our PCBs. So we directly start with our connector slide. You see a lot of connectors on the picture now, but those connectors are suitable for low currents, for signals, for example. Some of them are already suitable for power like 100 watts, for example. The new USB-C, you can deliver 100 watts at maximum. But what about higher currents than 50 amps or 100 amps? There are no more connectors left to put on your PCB to use it for those high currents. We need another solution for this. And therefore, I want to introduce you in our series. It's called the REDCUBE series. What is REDCUBE? REDCUBE is a terminal for the PCB to transport high currents either from PCB to PCB or from PCB to a cable. So we have different technologies in the REDCUBE range. We have the Pressfit technology. This technology is suitable for currents up to 500 amps on copper bars and up to 300 amps on the PCB. So we want to talk about the Pressfit technology today in our webinar. We have also some special Pressfit parts like the REDCUBE plug. You can see here on the left on the picture. REDCUBE plug is also a Pressfit part, but it's comparable to a plug. So you have a plug and play system with a Pressfit technology on your PCB. For currents up to 85 amps, we also offer some REDCUBE THR products, but for the THR products, we will not have a deeper introduction here in the webinar today. Therefore, I would suggest to listen to the webinar recording we have for THR soldering on our website. And we also have some SMD REDCUBEs. Those SMD REDCUBEs are suitable up to 70 amps. Why only up to 70 amps? Because they are soldered only on the top of the PCB. That means they are only able to contact the first layer on the PCB. So you have to go for some vias on the PCB if you want to transport your current in the other layers. So that's the reason why they are limited up to 70 amps. But we will talk about the high currents today, so we will talk about Pressfit technology. But Pressfit technology, not everybody knows how it works, so I will show you a little bit what's behind the Pressfit technology. Okay, you have a Pressfit element. This Pressfit element is made out of brass. Then you have a small copper layer, and on top you have a small tin layer. And this element is pressed into the PCB. The PCB, you have a copper via inside, and the pin of our Pressfit element is a little bit bigger than the via in the PCB. So you have a Pressfit connection there, and if you put it together, if you press it together, you reach a cold welding situation here between the via of the PCB and between the material of the element. So this is a solder-free connection. Please do not solder Pressfit elements. Pressfit elements are not suitable for soldering. You have many problems if you try to solder Pressfit elements. So the first problem is after you press it in, you bring a lot of stress on your PCB, and then you heat your PCB again, and the PCB gets really delaminated. That means the laminate is going, is not okay after the warming process. So please do not solder the Pressfit elements. The next thing is they are not made for soldering. They have a copper underlayer and not a nickel underlayer as a soldering product. That means if you go with those elements through the reflow oven, so the tin will just drop off the element and make some shortcuts on your PCB. So please do not solder them. For soldering, we have the THR or the SMD products. Okay, we have now a cold welding situation here from the Pressfit technology, and this cold welding situation gets absolutely gas tight. Gas tight means that no molecules can come in between our Pressfit connection during the operation. So we reach a powerful electrical connection with a very low resistance to the PCB. A low resistance is always a good idea when you want to transport high currents, because you get no additional warming on this case because of the low contact resistance. But how is this certified? There is also a standard behind. The standard is the IEC 60512-2-1. And it means that you do a contact resistance measurement with the tools you see on the right side over two REDCUBEs. Two REDCUBEs are measured, and then it's divided by 2. So if you have a usual soldering power connector, you have a resistance lower than 20 milliohms. But when we look to Pressfit technology, it's a lot of lower. It's below 200 microohms. So this is a really, really low resistance. And what's the advantage of a low resistance? Less contact resistance gives less temperature rise, means you have no additional warming from the element, from the Pressfit element on your PCB. So when we look at the Pressfit element themselves, we have 3 different types of Pressfit element. One Pressfit element has 2 rows, as you can see on the right side here. Another Pressfit element is the circumference, and another one is the full plane. That means the first one has 2 rows of pins. The second one, the pins are going around the element. And in the last one, it's fully assembled with some pins on the bottom side of the element. Why do we have 3 different types of elements? The first type, the 2-row, is okay if you have some copper in your PCB and you want to transport the current from one side to the other. Just bring it in the PCB, bring it on your copper track, then you need a 2-row element. With a circumference element, you are able to transport the current all around the element. So if you have a lot of copper in your PCB, then you can use the circumference element. Or even if you want to screw something from the bottom side into the element, it's also possible with the circumference one. If you want to screw from the bottom side, you need to have a full plane. This is not possible. Where do you need a full plane element? A full plane element is made for if you need high holding forces on your PCB, high mechanical forces on the PCB. Therefore, you need the full element because it has a lot of pins, and each pin gives you some holding forces on the PCB. You can also see on the table here some derating curves for the circumference ones. And there you can see that everything ends at 150 degrees Celsius. Why does everything end at 150 degrees Celsius? This is quite easy. We have a FR4 material in our PCB, and this material is only suitable up to 150 degrees. So every derating curve ends at 150 degrees for our Pressfit elements. So we talked about mechanical forces, we talked about holding forces. So how is this certified by the mechanical way? Therefore, we have to do a so-called pull-out test. So we screwed something into the element and try to pull it from the PCB again, and there you can see the graph on the right side, what happened. And we found out that it has an extraction effort around 10 kilogram per pin with a PCB of 1.6 millimeters. And you can imagine if you have an element with 25 pins and 25 multiplied by 10 kilograms, therefore you need 250 kilograms to bring it out of the PCB again. So in this case, you will destroy the PCB, but you will never be able to pull it out again. So it has strong mechanical forces holding the PCB with a Pressfit element. So I've got also some evidence for this. For our evidence, we made a test. You can see here a kind of special pull-out test. Therefore, we took a PCB. This is a 2.4 millimeter PCB, and there is a Pressfit REDCUBE inside, as you can see here. And this Pressfit REDCUBE is screwed into this triangle system. That means the triangle you can see here on the picture is only mounted on one single REDCUBE on the PCB. And the PCB is mounted on the metal part here. And now I show you a small video. Please enjoy. So this guy has at least 75 kilograms. So you can see that are really, really strong holding forces in our Pressfit elements. And there is no, you do not have to have any fear to get the Pressfit element pulled out of the PCB again after a proper Pressfit process. But now we have to look for a proper Pressfit process. What do we have to take in consideration when we want to establish a perfect Pressfit connection? First of all, we have to make a hole in our PCB, a drill hole, and this drill hole has to be 1.6 millimeters. It may be a little bit bigger than 1.6 millimeters. There's a plus tolerance of 0.03 millimeters, but not smaller than 1.6 millimeters. There is no minus tolerance. Why is there no minus tolerance? This is quite easy because our pin diameter is 1.6 millimeters. And when we make the hole smaller than 1.6 millimeters, we just press into the FR4 material. And we want to avoid to press into the FR4 material. We want just to press in the copper material. So we have to establish the drill hole with a 1.6 millimeter hole. Next step, we have to bring in our PCB some copper. So the minimum we have to bring in is 25 micrometers, but optimum is between 30 and 40 micrometers of copper. But be careful, the more copper you have inside your via, the harder is the Pressfit process at the end. Okay, now we have a little bit copper in our via on the PCB. And what do we need else to protect the copper from oxidation? We need a little bit of tin, a small tin layer. So this small tin layer brings us to an end diameter of 1.475 millimeters, and this is the value for chemical surfaces. So the optimum surface in your PCB for Pressfit connection is chemical tin. And when we look at the chemical tin surface, we have a diameter of 1.475 millimeters at the end. And this is the optimum for the Pressfit technology. So then you get a proper cold welding connection here at the edges of our PCB. The maximum tin we bring on our copper now is 15 micrometers, but optimum is only 2 micrometers. Why do we put only 2 micrometers on it? It's just because of the Pressfit process itself. So when you do the Pressfit process, the tin will be removed at the side of the element itself and will drop down, and so you do not have a lot of tin in your Pressfit connection when you have only 2 micrometers on your layer. So you can see here a real picture. This is a cut picture. There's also some resin inside in between. There you can see the Pressfit connection, how it worked. You see the copper ring here, and the element is directly pressed into the copper. And here at this point, you see the cold welding connection, which gives us a very low resistance to our PCB. So how does it work? We have the element, we press it into the PCB, into the vias of our PCB. It looks like this. I showed you this picture already in the last slide. And if we have a closer look at the corner of a Pressfit process, it will look like that. And there you can see perfect the cold welding situation. So this is the brass material of our pin. This is our via in the PCB with a copper inside. And here is our thin copper layer in the pin material. And what you can see here is a homogeneous cold welding situation between copper and copper. So this means those materials are the same, and there is no resistance between those materials, and the molecular structure gets better the longer the Pressfit connection stays. So you will have a really, really good, powerful connection without any big resistance here. And what you can see here, those knobs are the tin. The tin is just pressed away a little bit to the left and to the right, and you get the cold welding situation between copper and copper. And that's the big goal of the Pressfit technology. Okay, now we know how the Pressfit technology is working, and we know how to press it into our PCB, but how can we design our copper tracks in the PCB? Are there any rules for the Pressfit technology, how to design the copper in the PCB? Unfortunately not. But therefore, Würth Elektronik delivered something like a rule of thumb. So how does this work with a rule of thumb? You just take the width of your element. For example, you have an element with 6 millimeters, and then you multiply it with 3. So you need a copper track width of 18 millimeters in this case. And when you look at the thickness, the copper thickness in your PCB, it should be the rated current you want to transport on your PCB divided by 0.3, and you get the result in micrometers. Okay, I will give you an example for that. So here we have an element which is 7 millimeters width, and the 7 millimeters multiplied by 3 are 21 millimeters. So the copper track width on the PCB at the end is 21 millimeters. Now we have a look on the thickness of the PCB, and therefore we need the 100 amps. We want to transport the 100 amps. You can see here the value is 100 amps. And this divided by 0.3 gives us a value of 330 micrometers. How can we reach 330 micrometers thickness in the PCB? Or we can use 4 or 5 layers with 70 micrometers, or we can use 3 layers with a maximum of 105 micrometers of copper inside. When we look at the possibilities to put copper in the PCB, we have some standards behind. We have 18 millimeters, 35 millimeters, 70 millimeters, and 105 millimeters. And for the most PCB materials, 105 millimeters is the most possible to bring in one layer. So you can use it with 3 layers of 105 micrometers or 5 or 4 layers with 70 micrometers. But when you did this, you always have to do a temperature rise test with your prototype. Therefore, you just check it with current on the PCB, and your test goal is the heat repetition to verify the trace design and the numbers of layers, which influence do they have on the transport of our current. So we do the temperature rise test with a thermal camera. And we take the example I just gave to you. The working current was 100 amps. We have 4 layers in this case with 70 micrometers and 21 millimeters wide track. And the ambient temperature before the test was 21 degrees Celsius. And when you look at the picture of the thermal camera, and especially on the bottom view, we will see that the point where the Pressfit element is not the hottest point. As you can see on the pictures here, the hottest point is in the middle of the PCB, or sometimes the hottest point is also on the cable. You have to respect to take the right cable for your test. But there you can see we have a maximum warming of 42.4 Kelvin, and this is absolute okay for our Pressfit connection. So we proved that the rule of thumb did a good job and worked, and we can use our PCB as we tried it in this way. That means the rule of thumb design gives a good temperature balance for the full system, and the Pressfit connection do not bring additional delta T, additional warming. But please do always test when you do the first prototyping after using the rule of thumb. So therefore, we did another temperature rise test with different cable sizes. We have one at the first point, we have the cable with 10 square millimeters. And there you can see the warming is a little bit higher than when we use a bigger cable with 16 square millimeters. So for example, with 16 square millimeters and the same PCB design, we have a warming of 48 Kelvin, and with a 10 square millimeter cable of 64 Kelvin on the PCB. That means the cable is also able to cool the PCB to transport the heat away from the Pressfit connection. So REDCUBEs are small. They are able to deliver high currents. They are able to cool down the PCBs. And the rule of thumb, high current design is a good approach, but always check the temperature with prototype testing. So now we know how to create our tracks on our PCB. And now we have to look a little bit deeper on the Pressfit process itself. So you need some special materials when you want to do Pressfit technology. And therefore, we have a look at this slide. You need a PCB, you need a support. A support is very important for the Pressfit technology, not to break the PCB during the Pressfit process. You need also a base, a stamp, and a press. Let's have a look at the Pressfit process itself. Let's say we have a chemical surface on our PCB. Chemical tin is the optimum. ENIC is also possible, but not so ideal. And if we have a chemical surface, we can go to a drill hole of 1.475 millimeters. It's a very precise drill hole because we have a precise plating on our PCB. It's always the same thickness everywhere you have a look on your via because of the chemical plating. It's a little bit different when you have a Hall PCB, a hot air leveling PCB. There, the PCB is only dipped into the tin bars, then put out and and blown a little bit the tin away. And then you can see you have different sides of tin in your via. Sometimes it can be a little bit thinner, sometimes it can be a little bit thicker, and therefore we have to use another diameter for the Pressfit process. It cannot be so precise because the PCB is not so precise. You see you have different thicknesses inside here. So therefore we go to 1.45 millimeters plus minus 0.05 millimeters. And on the beginning of our presentation, I told you it's also possible to press into a copper bar instead of a PCB. Therefore, we also have a drill hole recommendation. It's this one. In a pure copper bar, you have always some oxide inside, and to remove the oxide, you cannot have a very precise drill hole specification. So we go also to 1.45 millimeters plus minus 0.05 millimeters. So with this situation, you can press into a copper bar and transport your whole current over the copper bar, and in this case, up to 500 amps. But there are a few things we have to respect for the Pressfit process itself again. For example, the thickness of a PCB has to be in between 1.6 and 3.2 millimeters. Why? It's just because of the length of the pins. The pins are 3.8 millimeter long, and this is suitable for a 3.2 millimeter PCB. PCBs smaller than 1.6 millimeter are not so suitable to bring a lot of copper inside to transport high current, so they are not suitable for high current applications. So we decided to go for 1.6 millimeters to 3.2 millimeter PCB. When you do the Pressfit process into your PCB, you have to respect that you put other SMT and THR components at least 4 millimeters away from the Pressfit element itself. Why? Because you get a little bit bending on the PCB when you press in your Pressfit element, and therefore, if you have some capacitors here, like the small SMT capacitors, they can have cracks after the Pressfit process. So therefore, stay away for at least 4 millimeters from other SMT components with the Pressfit element. When we look to the side of the corner of the PCB, we should stay 3 millimeters away from the corner of the PCB, just because of not bending and not breaking the PCB during the Pressfit process. How does it work? It's quite easy. A small video how the Pressfit process is done. So quite easy, no rocket engineering, just pressing in with a small hand press. But we need a good support. So if you do a prototyping, you can use a support from the 3D printer, as you can see here on the left side of the picture. I also have one. I show it in the camera here. It looks like that. It's a very soft material, so you can press in a few Pressfit elements, but after that it gets destroyed, so it's just for prototyping in this case. But how big should the holes be? They should be 1.75 millimeters with the tolerance you can see here. But there are also professional supports available on the market. You can see here a metal finalized version. I can show you also this version to the PCB. To the camera, it looks like that. And these supports are available at different companies directly for the Pressfit process. But you also have to take care that you fix your PCB on your support so that the holes are always under the element to get a proper Pressfit process. And in the real case, you can also have a support like this. If you have some SMT parts on the bottom side of the PCB, you have to take care for the SMT parts, not to press on them. So therefore, the Pressfit support can also look in this case like this one. It's made out of metal. What do you need else? You need else the stamp, because those Pressfit elements are made out of brass. They are not made out of steel. They are not so hard. So that means if you would press on this element here, you would destroy a little bit, and after that you cannot bring on the screw again. So it's not a good idea to press directly on the thread here. So you should press on the element itself, and therefore you need a stamp which looks like that. When we look at the two-part elements, we also have a stamp and a support. I will show you how the two parts elements are mounted. First, the ground element on the top of the PCB. Then the PCB is turned around and the ground element is supported. And then the support element comes from the bottom side into the ground element. So this is the way how the two parts elements are mounted on the PCB. What else? You need a stamp when you have an element like this, not to press on the corner of the element, to press on the total element. Therefore, you need a special stamp which has a shape, as you can see here on this slide. And we also have some recommendations regarding the presses itself. There are two companies in Germany where you can buy proper presses, and also the tools additional to the press you can buy from our company, and they fit to Schmidt pressen, and they fit to Gechter press. And how should I buy the right dimension of the press? How can I look for that? Therefore, I have to have a look on the insertion force. And the insertion forces you will have on a table here, but you can also find this on a Pressfit guide we have on our website. You can download the Pressfit guide on our website by yourself if you like. So here I can give you also a small example. Let's say we have a PCB 3.4 millimeters and we have a chemical tin. And then we have a REDCUBE with 12 pins, and 12 times 140 gives 1.7 kilonewton or 1,700 newtons, and it's slower than the press effort. And then when you multiply the 12 pins with the 340, it gives you around 4,000 newton or 4 kilonewton. So the press effort is in between 1.7 and 4 kilonewton. And then you say at the maximum you need 4 kilonewton in your press to put in this element. So therefore the press dimensioning should be 20% above, should be 20% security inside. So please buy a press with at least a force of 5 kilonewton for this case. So this is how you can dimension your press quite easy. And another few things to respect during the press fit process is the gap. You should leave a gap between the element and the PCB of 0.1 millimeters. Why? Because there can be some tolerances in the PCB. And if you use an automatic press and the automatic press does not respect the tolerances and the PCB is a little bit thicker than it should be, you can destroy the PCB during the press fit process. Therefore, you should adjust your press and stop when you use a manual press. The next thing is the flat zone of our pins should be visible outside of the PCB after the press fit process. Why? Because then you are sure that you have contacted also the last layer in the PCB. Because we have some flat things here on our pin at the end, just to bring in a better press fit process. But this one has to look out completely out of the PCB to be sure to contact the last layer of the PCB in the proper way. What about the insertion speed? It should be between 100 and 250 millimeters per minute, and the insertion should be done in one press fit process. At the end, I want to show you also some cable lugs we offer and some plugs for our REDCUBE plug system. And we offer also the tool, the hexagonal crimp tool, to crimp those plugs on the right cable to use it for the press fit technology. And at the end, I will show you some examples for press fit technology in the field. So the first picture is a double side mounted PCB press fit from both sides of the PCB. And also a good idea is the so-called laminated fuse. Because of the low resistance to the PCB you have with the press fit elements, you have an exact working, a precise working of the fuse for here in this case, in this example, at 80 amps. So if the current reaches 80 amps, the fuse blows at 80 amp, not at 81, not at 82, because of the low resistance we have on our press fit elements here. Also a good idea with press fit elements is an IGBT connection for switching high currents, or a board-to-board connection. This is from a welding system from a customer with a welding machine, and it gives a board-to-board connection with 200 amps from one board to the other, and also a precise mechanical stable connection. Here you can see a copper bar distribution where the current is distributed over some copper bars using our REDCUBE plug system. And the last picture I will show you is REDCUBE in the air. So also on microlight airplanes, we also use the REDCUBE terminals. So this proves you that the REDCUBE terminals gives a really, really stable connection to the PCB on the corner. So in this case, this constructor is Tony Roth. He's doing electric planes, and the 12 REDCUBEs, they deliver 1,700 amps for 7 minutes during starting process. And after that, you receive 1,500 amps regular for flight over 12 REDCUBEs. And this application is redundant. So if one system fails, 6 REDCUBEs also deliver around 900 amps for a safe landing. So you can see that the REDCUBEs are a really, really good idea when you have high currents on your PCB. And I hope you can you could join the webinar. And now I'm ready here, and I'm excited to wait for your questions. Thank you so much.
Yeah, thank you, Stefan, for your interesting presentation. Yeah, as you have
Welcome.
mentioned, now we would like to turn our attention to your questions. And so we wait a little until some questions come in. Also, just a hint from my side, you will receive the link to the presentation as well as to the recording of this webinar only in the next few days. Okay, Stefan, then let's start with the first question. If I have enic plating on my PCB, is Pressfit still possible? And are there any disadvantages?
Okay, enic plating is not the best thing you can do if you want to use a Pressfit technology, but I know a lot of components have to have an enic plating on the PCB, and sometimes, in some cases, it's not possible to have a chemical tin surface on the PCB. Then you have to use enic, and you can do a Pressfit process also in an enic PCB, but the forces are a lot of lower. Then you have to take care for the mechanical forces. They are not that high as they are with a tin surface, because the cold welding situation is not that good, not so good cold welding situation as in a chemical tin PCB. So it's better to use a chemical tin surface, but it's possible also in enic. It has a little disadvantage regarding the mechanical forces.
Okay, thank you for the explanation. Then I see the next question here. My PCB is 4 millimeters thick. Does Pressfit still work?
Yes, for 4 millimeters PCBs, we can do a special Pressfit element for you, a customized element, which is a little bit longer than the normal ones. The normal one, as I told you, they are 3.8 millimeter long, and in this case, we can do a Pressfit element with 4.4 millimeters. But from this point, we have to take care a little bit on the length of the pins, because during the Pressfit process, if the pins are too long, they can also get bent. So thicker than 4 millimeter is not a good idea. 4 millimeter is still possible.
Okay. Yeah, then let's go on. Do you recommend a manufacturer for the support?
For the support itself, yes, we also do recommend manufacturers. There are, for example, when you buy a press at the Schmidt Pressen, they can also give you ideas of support. But we have also one other company which is only doing support in Germany. They're called Schneid GmbH, SCHNAIDT.GmbH. At the internet, you will find this company, and there you can buy proper support for the Pressfit technology.
Okay, then let's go to the next question. I can see here for now just a hint from my side. If you still have any other questions after the webinar, you can also just email us at isis-webinar@we-online.com. Okay, Stefan, next question. Do you offer cable lugs for Pressfit?
Yes, you can find the cable lugs for Pressfit in our assembly portfolio on our website directly. They are made out of the same material as the Pressfit element itself, so they fit perfect to the element itself.
Okay, thank you. Yeah, then we have a short look at the next questions. Also, the hint from my side, at the end of the webinar, you will be asked to participate in a feedback survey. Of course, we would be pleased if you take the time to fill out the survey and help us. Okay, Stefan, I think I see the last question for now.
Okay.
Yeah, Stefan, is it necessary to have more press fitting tools, manual, automatic, for different shapes or connectors? And what is the approximate cost of the fitting tool?
Yes, you can, let's say it like this, you can buy one press, and you can buy different stamps for different connectors, and you can use the same press for for IDC connectors and for Pressfit technology, when you have just to use different plates, different base plates and different stems for that. So the price of a press is around 1,500 euro, only the press, and then you have the base plate. It's around also 500 to 600 euros, and you have the stamp around 100 euro. And this base plate and the stamp sometimes have to be changed. So it's if you want to do another connector, you have to buy some tools for around 600 euros. But you can use the same press. You do not have to buy a base press every time, a new one. You can use the same one. It's around 1,500 euros, and then buy only the base plate and the stamp additional to the connectors.
Okay, so thank you very much. Now we are finished with our webinar. And yeah, thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Stefan, for your time today.
I also have to say thank you very much and wish you a great day. Bye-bye.
Also from my side, have a good day. Bye.